So the last lesson in Module 10, this is going to be assessing visual overlap. And as you can see, our learning target, I can assess the amount of visual overlap between two distributions to make comparative inferences about two populations. And the vocabulary that we are going to learn is visual overlap. I have written a question down, so we are going to start with this one. And let's see. All right, here we go. Now, so we have learned how to make inferences about two populations by comparing the centers and variations of the sample distribution. Okay. Now, you can also make inferences about how likely it is that the means of the populations are similar or different. Okay. So we're going to use this as an example, to discuss what I just said. All right. So let's look at this question. And it's saying a local veterinarian, Dr. Gibson, weighed a random sample of male and female adult dogs. The results are shown in the double box plot. Dr. Gibson wants to know how likely it is that the mean weights of female and male adult dogs are different. So look at this one. It is a dot plot. I've just put the X, which is signifying the dot, so you can see this clearly. Okay. And so as you can see in this dot plot, the females are here, the males are over here. Okay. So to do so, Dr. Gibson can informally assess the degree of visual overlap between the two distributions. And the visual overlap shows the distance between the two means of the distributions as seen in the shaded section of the double dot plot. So again, the visual overlap is showing the distance between the two means of the distribution. Okay. And we can see that in this, I've just outlined it. So this is the distribution over here, the means. Okay. And now to informally assess the degree of visual overlap, we are going to express the difference in the means as a multiple of the measure of variability. Okay. So in other words, we are going to find and analyze the ratio between difference in means. Okay. Difference in means. So this is the ratio that we need to find over the mean absolute deviation. Okay, so difference in means over the mean absolute deviations. So as you can see, both the distributions are symmetric. Okay, we can see here, so on both sides, and then if you look over here, both sides. So these are symmetric in nature. And so we're going to find the means and mean absolute deviations. Okay, so let's look at the females. And we have, I'm just going to write it over here to find the mean. All right. So we have 2 times 60, okay, to find the mean over here of the females. Okay. So we have 2 times 60 plus 2 times 61. Plus we have 62, 1, 2, 3, 4, 5. 5 times 62 plus 263, and we have 264. Okay, and then we are going to divide this by the total number of the data set: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So we're going to divide this by 13. And when I do the calculations, I'm going to get 806 divided by 13 after adding all the numbers on the top, multiplying and adding. And so I get my mean as 62. My mean is going to be 62 for the females, okay? Now, let's talk about the males because you've got to find both the means. So, for the males, the mean of males, okay, this is going to be, now let's look over here, okay? So, we have 2 times 63 plus 3 times 64 plus 3 times 65 plus 3 times 66 plus 2 times 67. Okay, and then we are going to divide this by how many males there are, which is again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 divided by 13. And I get 845 divided by 13. When I do the calculation, I get 845 divided by 13. And so for males, I get a mean of 65. For males, I get a mean of 65. So the mean weights for males and females differ by how much? This is 65, this is 62. So if I do 65 minus 62, it is going to differ by 3 pounds. So it is differing, like the difference is 3 pounds. Difference is 3 pounds. Okay, now once we have looked at this, just by looking at the samples in the double dot plot, how likely do you think it is that the population means are different? So just by looking at the dot plot, okay? So I think it is likely, that the population means are different because both sets of data appear to have low variability and the data overlap. Okay, so again, there's low variability. Okay, it's like pretty much clustered together. And again, the data do overlap. Okay, so that's why the population means are going to be different. So now after this, once we have calculated the means, we are going to calculate the mean absolute deviation. And the mean absolute deviation is basically how far is the number from the mean, of the data set. And we have done that in this unit earlier on. So I am not going to again show you in depth how to do that, but I'm going to go ahead and just quickly do that calculation on the top. So let's do the ones for females. I'm just going to write this on the top so you can see what I'm doing. So mean absolute deviation now. Mean absolute deviation. Okay, so we're going to see what was the mean for the females. It was 62, right? So now we are trying to see how far is each number from 62 over here. Okay, so this is the thing. So we'll see how far is 60 from 62, how far is 61 from 62, how far is 62 from 62, how far is 63 from 62, how far is 64 from 62. So basically that's what we're doing. You're trying to find the mean absolute deviation, and we can see we have two numbers that are 2 away from 62, right? So 2 times 2, we have 2 times 2 plus we have two numbers that are 1 away from here. So it's going to be 2 times 1, okay? Plus, this is the same thing. There's no distance because there are 5 of them. Add 62, 1, 2, 3, 4, 5. So 5 times 0. Okay? And then we have two numbers that are 1 away from here. So 2 times 1 plus we have two numbers that are 2 away. Two numbers that are 2 away. Okay? And then we are going to divide this entire amount by 13 to see the mean absolute deviation. And I get 12 over 13. Okay, and 12 over 13, and so that gives me about 9200. So that gives me about 9200. So this is my mean absolute deviation of the females. Okay, in the same way, I am going to calculate the mean absolute deviations of the males. Okay, so for the males, I'm going to write that here. Okay, the mean absolute deviation. And we can see that in males, what was the mean? It was 65. Okay, so we are seeing how far is 63 from 65? That is 2, right? The distance. How far is 64 from 65? That is 1. And 65 in here, there is no distance. That would be 0. And then we have 3 of them that are 1 away from 65. And then we have 2 that are 2 away from 65. So when we do that calculation, we are basically going to get, just do this over here, 2 times 2 plus 3 of these are 1 away. So 3 times 1. Okay, and then I have 3 times 0. Okay, because 3 of them. So plus 3 times 0. Plus I have 3 of these are 1 away, so 3 times 1, plus then I have 2 of them that are 2 away. So 2 of them are 2 away from here, okay? And then we divide this whole thing. Again, there are 13 data pieces. So when I do the calculation, I am going to get, in this case, I'm going to get 14 over 13. And so that gives me my mean absolute deviation is about 1 and 800. So here is my mean absolute deviation for the males, and that is the, I hope you can see that, 1 and 800. Okay, so 1 and 800 is for males, and 9200 over there is for the females. Okay, now we are going to find the ratio once we have this. So to the nearest whole pound, the variability, mean absolute deviation of each distribution is 1 pound. Okay, so this means the average distance each dog's weight in the sample is from the mean is 1 pound. And the distributions have similar variability but different means. So we're going to find the ratio of the difference in means. Okay, so we are going to find the ratio of the difference in means over the mean absolute deviation. And what was the difference in means? The difference of means was this much, which was 3 pounds, right? So we are going to write 3, which is the difference in means, over the mean absolute deviation is going to, means are separated by just 1. Okay, so by 1. So, or we can also call this or 3 meds. Okay, or 3 meds. So here we go. You can write it like this. And that is the ratio that you have over here. Okay, so once again, to the nearest whole pound that we're talking about, the variability, which is mean absolute deviation of each distribution, is 1 pound. Okay, so here this is 1 and this is 1 to the nearest whole number. Because that's going to round, this is going to round to 1. This is going to round to 1. So that is why I'm talking about the mean absolute deviation is 1. Okay, and so now let's look at that again. Difference in means is 3 over 1 or 3 mads. Okay, now make sense of the phrase the means are separated by about 3 mads. And what does this mean again? The means are 62 pounds and 65 pounds, so they are separated by the difference, which is 65 minus 62, and that's why you get 3 pounds over there, okay? And then the MAD is 1 pound. So the means are separated by 3 MADs, and that's basically what it means, okay? Now, um, so we are going to analyze this ratio now. When the variability is small, such as 1 pound, the data are less spread out and are more consistent. Dr. Gibson can have a higher confidence in making an inference that it is likely the means are different. Because the sample means are different and the variability is low, and the ratio difference in means over MAD takes both of these into account. Okay, so the greater the ratio, the more likely it is the means of the populations are different. So the greater the ratio is, there's going to be more difference in the means of the populations. And so in this lesson, you will basically use, I'm going to give you some sample distributions to informally assess how likely it is that the means of the populations are similar or different based on this ratio. Okay, so actually, let me just put this up on the board for you so that it is easy for you to comprehend what I am talking about. Okay, so let me just come over here. You can see my board. All right. So let me go back a little bit, I think. So here we go. So this is what I wanted you to look at, which is the sample distributions. Okay, so let's look at this. And so once again, let me discuss what I was just saying, that the greater the ratio between the difference in means and the mean absolute deviation, that means that there is going to be there is going to be a greater ratio, so the means of the population are going to be different, okay, are more different. So let's look at the sample distribution. When you have the ratio over here, difference in means over MAD, if it is less than 2, if it's less than 2, the separation between the samples should be less noticeable. And so the means of the population in this case is more likely to be the same. Okay. However, when it's greater than 2, it will be more noticeable. So when you're looking at that ratio, it's going to be more noticeable and more likely to be different. Okay, so in the ratio that we just did, which is 3 over 1 or 3 MADs, because 3 is greater than 2, the separation between the samples for males and females is noticeable, and the mean weights of the male and female dogs are likely to be different. Okay, are likely to be different. So this is one thing I just wanted to quickly grasp. So if it's less than 2, it is going to be less noticeable. If it is more than 2, it is going to be more noticeable. So therefore, when we look at the mean that we just calculated, the ratio of the difference in mean to the mean absolute deviation, we definitely got that the males the ratio was 3 over 1. So that is why it is going to be more noticeable in this case. Okay, they're going to be different. All right, now let's look at an example, and let me give you this one. All right. So the double dot plot shows the daily high temperatures of 2 cities from 13 randomly chosen days in July. Okay, the table gives the mean and mean absolute deviation for each city. All right, so you can look at that. And we are looking at the data over here. Both of those plots are symmetric. Okay, so as we can see, now here is what I have, because the mean absolute deviation and your mean has been calculated. Okay, so for Fairview, your mean is 82. Okay, and for Silver Lake, your mean is 84. Remember, we are basically accounting how many they are in each. So this is 78 times 1, 79 times 2, 80 times 2, 81 times 3, 82 times 2, 83 times 2, 84 times 1, etc. in order to find the mean. And then we are dividing by how many items there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is dividing by 13. And that's how we are getting this mean of 82. All right. And the same way, when we calculate this mean, we are going to get 84. And then the mean absolute deviation, when we are looking at the difference in the means, all right, and we are going to divide that by the mean absolute deviation. So what am I going to get? I'm going to get 84 minus 82. Okay, so I'm going to look at the difference in the means. So again, my ratio has to be difference in the means over the mean absolute deviation. So that is the ratio that I need to follow. Okay, so if I'm looking at this, what are the difference in the means? I have 84 minus 82 over the mean absolute deviation, which is 1 and 4/10. So 84 minus 82 is 2 by 1 and 4/10. And when I simplify this, I get about approximately 1 and 43 hundredth. 1 and 43 hundredth is my ratio. Okay, so the means are separated by about a 1 and 43 hundredth measure of variability. And so if I'm making an inference as to whether or not the means of the two populations are likely to be different, using the conventions provided earlier, in the earlier slide, I was talking to you about that. A ratio that is less than 2 indicates that the means of the population are likely to be the same. So let's look at this one. We have the ratio here is 1 and 4300, which is definitely less than 2. Okay, it's definitely less than 2. So because of that, it is likely that the average high temperature in July is the same for each city. All right, it's the same for each city. And so is it possible to infer that the means of two populations are likely different when their dot plots overlap? And yes, because it is possible that the means of two distributions are separated by more than two measures of variability, even if they show some visual overlap. Okay, for example, a small number of samples with the greatest value in one distribution might overlap with a small number of samples with the least value in the second distribution. So when that happens, yes, there is going to be that difference. Okay, so once again, to assess visual overlap, please remember you're taking the data set, you are finding both the means, and then you're finding the difference of the means. And then you're also finding the mean absolute deviation of each of those. And then you're finding the ratio of the difference in means over the mean absolute deviation. And if that, if the ratio is going to be less than 2, then there should be, what do you call it? The separation between the samples will be less noticeable in that case, and the means of the population will not be that different. But if that ratio is greater than 2, then there will be more of a difference in the more of a separation in their means from each other just by looking at that ratio. So whether you can see if the means are going to be similar or different based on the ratio that is provided. So it should be less than 2, okay? If it's more, there's going to be more of that difference. All right? So that is what this lesson is, and that completes module 10, sampling and statistics. Have a fabulous day, everyone.